So, good morning, everybody. It's a pleasure to be here and to have the opportunity to share the floor with Brian and to tell you more about how the quantum computers that we have built based on manipulation of photons, based on the manipulation of light in Candela, can be used for industrial applications in collaborations with Brian. Brian?
So hi everyone, nice to meet you all here. My name is Brian Ventura, so PhD in physics, and I'm a research and application scientist at Sigma Reply.
So just maybe one word of context about, well, it's very small, about these collaborations. It started 1 year ago, and we are very proud in Candela to have met the teams of Sigma Reply. Actually, it started so because we realized that there are many use cases to explore, and in Candela we have this strong expertise in quantum based on the manipulation of photons, but we wanted to go further and to work with people that have strong skills in the development of applications and softwares. And we have met the teams of Sigma Reply, and since then we have built a very strong partnership. But maybe you can tell us more about you.
Sure, so you might not all know about Reply, as Candela at least. So the Reply group is a group composed of 13,000, well, more than 30,000 people across the world. So you see that we have an international presence, essentially in Europe. So the roots started in Italy, and so we are mainly based in in Italy, of course, Germany, France, UK, Benelux, and also we have presence in America, in Asia. And initially, the service offer of Reply. So Reply is a consulting group in IT with applications in various sectors from energy, healthcare, logistics, finance, and so on, many others. As for the quantum computing experience in Reply, so it all started in 2018. And since then, so the Reply group has participated in many conferences, many hackathons. And in 2022, Olivier Debicki created the business unit called Sigma Reply, which is specifically dedicated to quantum computing, with the partnership we did with Candela this year. And that's for the latest achievements. So we recently participated to the QHack 2023. Where we won actually a prize in quantum chemistry simulation with alternatives to variational algorithms for those who know what I'm talking about, and also in hybrid algorithms.
So you have heard about Candela in the previous sessions, but maybe I can enter into the details about what we do in Candela. So the company has been founded 6 years ago in 2017, and we have developed strong skills in the development of new technologies based on semiconductors and light. I will explain a bit more. And what we do now, we have now in the cloud, Mosaic. So Mosaic, it's assembling of unique semiconductor technologies. We use optical modules with strong and unique electronics. We also developed our own compilation stack and the computing framework and a simulator tool that I will explain. And this is called Perceval. Perceval is an open source programming framework with about 3,000 users, developers all around the world. It's used to host an algorithm toolbox that can be developed internally by Candela, but also by partners like Sigma Reply, for example. So we are very open to the community. This is why we decided to have this framework open source. This is why we decided to have the machines open in the cloud, and we can, with this, have access to the QPUs that are called Mosaic. So just a few words about how the machines work. There are two approaches for the digital quantum computers. The most famous is based on matter qubits, like ions, superconducting qubits, or quantum dots. These qubits are statics. They are very easy because it's easy to see them because they are physically fixed and located on a chip, like a QPU. And then you send instructions on this QPU. You control these qubits externally with some external electronics. The main advantage of this approach, it's easy to control the qubits, to have gates with the neighbor qubits. But there are physical size, which means that there is a limitation in terms of scaling up. And it means also that the optical connectivity is difficult. There is basically almost no optical connectivity. Plus, since they are matter qubits, they suffer from decoherence, leading to some errors with the qubits. On the other side of the spectrum, there are the photonic qubits that are based on light. So as you can imagine, we call them flying qubits because they travel at the speed of light. And we can actually encode the quantum information like very easily. For example, you take a spatial mode, which is here like these blue lines. So this is just a rail of where the light can travel. And actually, we can fabricate, you can emit one single photon, you manipulate this photon, and you define the 0 and the 1 qubit, and then you can play with the superposition of states for the position of these single photons between different modes in order to have the quantum information, the entanglement, and all the tools to run some computations. So now we have this image at a large scale. We can use large-scale interferometers that you can program. You can inject trains of single photons inside, and you can actually, with this, have the equivalent, or you can have a gate-based quantum computer machine. This is very advantageous because the qubits, the photons, are very robust. By nature, they are isolated from the environment. You can run the calculations at room temperature, and actually, the connectivity, the modularity, the scalability of the platforms is included because we use light and we use optical fibers to connect all the different modules. So in Candela, we exploit actually both of these two worlds. We fabricate very efficient emitters of single photons based on quantum dots. These quantum dots are fabricated inside optical cavities, such as actually you can have a high coupling and very efficient coupling between the external world with all the modules in order to control the quantum information and the matter qubits that can be used to have entanglement of qubit operations. And then with these photons, we generate those photons, we couple into optical fibers, and we manipulate the information into these very small photonic integrated circuits where you can have thousands and hundreds of these small interferometers that are used to control the information. This is basically what are inside the machines. Just to show, basically, you have the different steps. The A, you generate the qubits, then all these trains of photons are used and collected to manipulate the information at room temperature on these interferometers, and then you measure the quantum information using detectors. We have developed all these modules. We integrate everything. We have developed the feedback controls, electronics, and the operating system, which is used for the control of the machines, for the transpilation of the compilations. And now we are very proud to tell that everything is accessible and open to everyone in this room and even outside this room on the cloud. So we have developed a proprietary cloud hosted at this address, cloud.candela.com. And actually, with this, we can tell and we can assume the fact that these machines are available 24/7 with more than 95% availability. We have now released the performances of these machines, these gate-based quantum computers, in a scientific paper, which has been released a few weeks ago. And in this article, actually, we compared the performance of these machines with other machines that are also available in the cloud. For example, here I'm showing some of the performances that we have measured and that are now published. And we are showing that if we compare the platform of Candela with other platforms like IonQ or IBM-Q, the Keto processor, you can see that actually the fidelity of the gates that you can have with photons at room temperature is as high or even better than the other platforms that are known for this high fidelity. And also a very important topic that sometimes it's hidden in the development of the platform. So there is the fidelity of the gates, of course, but this is also the speed, meaning that how many gates you can operate in 1 second, corresponding to how fast will be the calculations. And here you can see that actually, compared to the other platforms, the photonics benefits from all the aspect that has been used and developed for all the telecommunication industry, which is basically you can manipulate and you can have many gates, about 100 times better than IonQ platforms, and leading that to a larger factor in terms of problem solving. So maybe I have discussed a lot about the technology and the performance of the machines. The other question is how can we control these machines? No, sorry. Just a catalog. And so now we have two QPUs that are available in the cloud. The first one has been released 1 year ago, which is called Akerna, with only 2 qubits, but a very strong application, which is the fact that you can use these 2 qubits, untangle them, and use this entanglement to generate quantum certified random numbers. These random numbers can be used for many applications like cybersecurity, communication, storage of data, and also other applications like Monte Carlo calculations or lotteries. And this is available online. It's also available on-premise, but we need to take the machine and deliver at the location of the users. But just to mention that this is very compact and very stable technology. And then we have this machine, Scala, which is, I mentioned before, with 6 qubits, which is a fully reconfigurable, very versatile platform that can be used for many applications. And now we are developing another one, which is called Altair. It's going to be more application specific, and it's going to be tailored for other applications like quantum machine learning, but applications that we will explore after the summer. So all these machines are available in the cloud. It can be controlled by using Perceval, our open source framework. So actually, in parallel of this session, we organized a masterclass, so difficult to advertise it, but we have now many users, developers using Perceval. This is a Python library dedicated for the photonic platforms, but this is also very compatible with all the environment, IBM's environment called Qiskit, which is one of the most used in the world for the gate-based platforms. And with this, actually, we can easily take use of these machines. We organize few hackathons, and during these hackathons, students or even users were able to develop algorithms in 2 or 3 days. And maybe you can give us some feedback about the use of the Perceval and the QPUs.
Sure. So with all that shown, we were actually very amazed by the full software stack that Candela provided, from the cloud access to Perceval to the run on actual QPUs. So we tried to work on a use case which was initially developed also by Candela on solving partial differential equations. So what we did is to develop a hybrid quantum machine learning model using, which leverages photonics at its essence. And the idea is to solve here, as you can see, the heat equation in 2 dimensions in space and in time. So you can see the evolution here as a function of time. And so we are actually soon communicating on this on the AWS blog. So stay tuned for that. As for the domains of applications, so we are pretty sure that this is actually relevant for the energy sectors, but we have actually see that this can be also used in financial services. For instance, when you model stochastic models with the Black-Scholes equations. Actually, the Black-Scholes equation is one of the many forms of the heat equation. So this kind of solving PDEs through photonics is actually very interesting also for finance services. And actually, the model built here is a quantum machine learning model, which can also be used for other things than solving PDEs. For instance, for performing machine learning tasks in general. And so we tried, we're going to try for other sectors such as automotive, where we can, for instance, perform automated quality assessment in this frame. So the pros of this model is actually it's deeply interpretable as a quantum machine learning model with respect to neural networks that you can already have in existing frameworks. The other thing, as I mentioned, is that it's highly versatile. So it can be used to solve PDUs or to perform classification tasks. And actually, what Valerian mentioned is actually very, very interesting. The article which was published by the Candela team in the 1st of June actually shows the usage of such model well, run on the QPU for classification tasks. So I just also want to enlarge a little the scope of the applications. So just to discuss about what we did before in Europe. So you can see, for instance, some optimization problems. So on the left side of the slide, you see an example of infrastructure maintenance, where you have to dispatch team workers across maintenance grid. So this work has been done with NL in partnership with AWS. So quite a success story. We also had some examples of other optimization problems in the train platforming problem, portfolio optimization with the Raiffeisen Bank International, and as I also mentioned before, so the automated quality assessment, which was done with the BMW group during the hackathon. So just to conclude, so maybe Valerian, you want to...
We are a bit late, so just to conclude, I hope we convinced you that now we have platforms available and we have a team with a strong experience in different topics, development of use cases, development of the hardware and software, such as actually you can now, don't hesitate to contact us in order to identify useful use cases, develop the models, and deploy this technology on operational platforms. Thank you.